In the previous video, we saw that 4CID focuses on the development of complex skills. In this video, we'll take a closer look at our cognitive architecture to see why we need to design in a certain way to help learners develop complex skills. What happens when we learn? We process information in a way that creates a change in our long-term memory. In our long-term memory, we store factual and descriptive things like concepts, plans, and principles. For example, you know the concept of a bird and you can list its general characteristics. It has a beak, feathers, can probably fly, and lays eggs. You understand what each of these things is. You probably have seen a lot of birds in your life, and when you hear the word bird, you now have a stereotypical or average bird in mind. Such generalizations help us store information much more efficiently, but like stereotypes can also mislead us. You also know plans or scripts, like the plan to have dinner in a restaurant. You know that you have to wait to be seated and that the waiter will ask for your order. And you know principles, such as the principle that fire is hot and touching it will burn you. Concepts, plans, and principles are linked to one another, like in a network or a framework. We call these structures cognitive schemas. Novice medical students know little about anatomy, so their schemas are very limited and unstructured. At first, the links to other elements will be weak. As they learn, more new information is processed and connected to their existing schema. Not only will their schemas grow, but they will also become more structured and organized. They learn how organ systems are related and dependent, how diseases affect different organs, and which symptoms predict which disease. And as the connections grow and become stronger, retrieving the right information at the right time will become easier. Retrieval means that elements from long-term memory are moved to working memory where we become aware of them. Our long-term memory is extensive and potentially unlimited, but we cannot be aware of everything we know at once. The general idea is that we only become aware of the activated elements of long-term memory. This activation spreads through long-term memory. When we activate one element in a schema, other elements of the schema, and potentially other schemas, will also activate if there are strong connections. But if there are a few connections or weak connections, it will be much more difficult for the activation to spread. So the more connections and the stronger the connections in a schema, the easier retrieval will become. The elements of the schema that are retrieved end up in working memory, where they become available for cognitive processing. However, the capacity of working memory is very limited. It can only store about 7 items if very little processing is needed, and even fewer if these items need to be manipulated in some way. But there's good news, because we know that when we create well-integrated schemas with strong connections, they only count as one element in working memory, making cognitive processing much more efficient. This process of schema construction is very important because it lowers the load on working memory. There's a second important process, but before we get to that, we have to talk about the other element in long-term memory, rules. Now, if you have an extensive schema about driving a car, you can explain how the car works and how one should drive it, but it doesn't guarantee that you can also drive the car yourself. So, how about the ability to actually do something? How is this represented in our cognitive architecture? Physical actions like operating a crane or riding a bike, but also cognitive activities like tax calculations or inspecting an X-ray. This type of knowledge, sometimes referred to as procedural knowledge, is expressed in rules that act on the activated knowledge in working memory. Rules are specific types of cognitive schemas that link a specific situation or condition to a specific action. Think of them as if-then statements. If I see a red traffic light, then I put my foot on the brake pedal and apply pressure. If I am approaching too fast, then I apply more pressure to the brake. As you can see, rules often rely on elements in our schemas because you cannot perform this rule if you don't know what the brake pedal is. Sometimes we learn to use a whole bunch of rules in a row. In these cases, a collection of if-then rules is combined into a procedure, which might look a bit like a flowchart. Naturally, procedures can be very simple, like the procedure to make coffee with a coffee machine, or very complex, like the procedure to shut down a nuclear power plant. By forming rules and procedures, we can automate the application of our cognitive schemas. This happens unconsciously by building experience and requires repetitive practice of the task. You cannot learn to drive a car or bike from a book. Only after driving the car time and time again will you learn exactly how far to move your foot, to put it exactly on the brake pedal, and how much pressure to apply to brake comfortably. Only after seeing many X-rays you will learn that if you are looking for a specific injury, then you need to scan the X-ray for specific signs. Sometimes you can reuse rules from one context in another when the tasks are very similar, but sometimes you'll have to generate new ones. If you drive a new car that is very similar, then your existing rules can be used. But if you drive a truck instead of a car, you'll have to create new rules that are somewhat similar, but more attuned to driving a big truck. Steering, braking, and checking your mirrors will now be different. Rules and procedure also lower the load on working memory. First, because behavior is now driven by rules, the underlying schemas no longer need to be present and processed in working memory. Second, when rules are often carried out in the same order, they can be chunked together into a single rule or procedure, making performance even more efficient. So now we know that complex learning involves two important processes: the creation of cognitive schemas that contain our concepts, plans, and principles so we can understand and reason about the domain. This is needed for the controlled aspects of the complex skill. And automating these schemas by creating rules that associate specific behaviors with specific situations. This is needed for automatic processing when performing a complex skill. When designing a program with 4CID, your aim is to stimulate schema construction and schema automation simultaneously while keeping within the bounds of working memory. To summarize, the performance of complex skills requires the presence of cognitive schemas and cognitive rules, and we need to make sure that we combine learning strategies that foster schema construction and automation in parallel. We'll talk more about this in the next video.